Next chapter that we're going to talk about and look at it real quickly is chapter 11, and this is dealing with energy and its conservation. This goes along with what we looked at chapter 10. So if we kind of look at the work energy theorem. So back in chapter 10 we were talking about this when we looked at this. Work done on a system, the energy of the system increases. Work done by a system, the energy of the system decreases. So kind of look at an example of this, throwing a ball. So if we throw a ball, it is doing work because we have force times distance. Now, throwing a ball, the force and the distance are in the same direction, so work is positive. And we can kind of deal with this in kinetic energy, and kinetic energy is going to be positive as well. So work done on the system, energy of the system increases. The ball, as the system, has work being done on it, so it is going to be increasing. Now, if we are catching a ball, the force in the direction are opposite, or the force in the distance, because the force is going to be going one way and the direction is going to be going the opposite, so work is negative. And actually what is happening when you're catching a ball or hitting it with a bat or whatever, the ball stops and has zero kinetic energy at that point because it stopped moving for that brief second. Okay, so kinetic energy, when we saw this was the last chapter, kinetic energy is equal to 1/2 times the mass times the velocity squared. Now, take note that kinetic energy is proportional to an object's mass and also the square of the object's velocity. Now, what if we were looking at something that was spinning like a top? Well, we can have what's called a rotational kinetic energy. KE rot, rotational, is equal 1/2 I and RW, which I represents the object's moment of inertia. And that W, if you kind of remember, is the object's angular velocity, since it's going around in a circle. Alright, so let's kind of look at an example of dealing with kinetic energy. So our first problem says an 875 kilogram car speeds from 22 meters per second to 44 meters per second while passing another car. What are its initial and final energies, and how much work is done on the car to increase the speed? Okay, so if we find our initial kinetic energy, so 1/2 mv squared, 1/2 times our mass, 875 kilograms. Now for this initial kinetic energy, we're going to use our initial velocity, which was the 22 meters per second. I'm going to square that. So if we take 0.5 times 875 times 22 squared, come up with 21,100, or excuse me, 211,750 joules. Now our kinetic energy, or final kinetic energy, mass still stays the same, 875 kilograms, but our final velocity is the 44 meters per second. Let's square that. So if we take 0.5 times 875 times 44 squared, come up with 847,000 joules of energy. Alright, so that's our initial and final energies. Now the last problem that we need to figure out, It says, and how much work is done on the car to increase its speed? So what we're going to just do is take the difference between our two kinetic energies. So we're going to take the final minus the initial, so 847,000 joules minus 211,750 joules. And that would be how much work is done. So our work done is 635,250 joules. Now, we do have what is called stored energy, or in other cases we have, it's called gravitational potential energy, or just potential energy. Now, the way that we represent potential energy is just with PE. Kinetic energy, KE, K standing for kinetic, E for energy, potential energy, PE. Now, with potential energy, we need to know this one thing. It's called the reference level. Now, the reference level is the height to which the object has risen to. The position is where the potential energy is defined to be 0. Okay. The way that we can calculate out the potential energy is we take mass times our acceleration and gravity times the height. So let's kind of look at an example of this. So it says you lift a 7.30 kilogram bowling ball from the storage rack and hold it up to your shoulder. Storage rack is 0.61 meters above the floor, and your shoulder is 1.12 meters above the floor. So we have a couple parts to this. So A, how much potential energy is in the bowling ball when it's at your shoulder relative to the floor? B, when the bowling ball is at your shoulder, what is the potential energy relative to the storage rack? And C, how much work is done by gravity when you lift the ball, and we got the other part right up here, from the rack to your shoulder. Alright, so let's work on A. How much potential energy is in the bowling ball when it's at your shoulder relative to the floor? Alright, so potential energy is equal to mgh. So the mass of the bowling ball is 7.30 kilograms. G, as I said, is acceleration due to gravity, 9.8 meters per second squared, times the height. Now, look back at the question. It says that at shoulder height, your shoulder height is 1.12 meters. So 7.30 times 9.8 times 1.12. We have potential energy of 80.12 joules. Okay, B says when the bowling ball is at your shoulder, what is the potential energy relative to the storage rack? Alright, so figure this one out. Still going to use mgh. So m 7.30 kilograms, g 9.8 meters per second squared. Now this time the height, since it says relative to the storage rack, our shoulder height is 1.12 meters, and the storage rack is 0.61 meters above the floor. So we're going to take 1.12 minus 0.61, excuse me, meters. Alright, so 7.30 times 9.8 times and 1.12 minus 0.61. And I'm coming up with right around 36.49 joules. C. How much work was done by gravity when you lifted the ball from the rack to your shoulder? Okay, so work, force times distance. Now since how much work was done by gravity, we're going to have a negative sign in front of this, so negative 7.30 kilograms times 9.8 meters. Then our distance again, so 1.18 meters minus 0.61 meters. So if we look, we're doing the same calculations that we did for B, but since we have a negative sign in front of it, our work done by gravity is going to be negative 36.49 joules. Now, two more things to kind of take note. Elastic potential energy. This is stored energy in pulled strings. So if you do any kind of archery competition or even in track when you see pole vault, the pole has some elastic potential energy. The string and the bow, for the bow and arrow, has elastic potential energy. And all this stuff can be converted. Then one other thing, if we're looking at rest energy, E ought is equal to mc squared. Okay, now where have we seen this before? Einstein came up with this. Energy is equal to mc squared, where m stands for mass, c is the speed of light, okay, speed of light, (2.998 times 10 to the 8 meters per second). And this takes us to the end of section 1 chapter 11. If you have any questions, let me know, email me, and I will talk to you later. Thank you.